The area under a curve is captured by definite integrals. Imagine a curve y equals f of x, bounded between x equals a and x equals b. Mathematically, we say area A equals the integral from a to b of f of x dx, that is, a is equal to integral from a to b f of x dx. If f of x is above the x-axis, this area is positive. But if the curve dips below the axis, the integral turns negative, and we must take the absolute value to get the geometric area. So always remember, the definite integral gives sine area, not just the raw size. Sometimes the region is better described with respect to the y-axis instead of the x-axis. For example, if the curve is given as x equals g of y, bounded between y equals c and y equals d, the formula becomes a equals the integral from c to d of g of y dy, that is, a is equal to integral from c to dg of y dy. This is especially useful when equations are written as x in terms of y, like in sine-wave parabolas. Depending on the curve, we choose integration along the x-axis or along the y-axis. Let's outline the two most standard cases. Case 1, area between y equals f of x, the x-axis, and vertical lines x equals a and x equals b. Case 2, area between x equals g of y, the y-axis, and horizontal lines y equals c and y equals d. In both cases, the idea is the same. We integrate the defining function with respect to the chosen variable. The boundaries a, b, c, and d are decided by the points where the curve meets the axis. Now here's a powerful shortcut: symmetry. If a function is even, meaning f of negative x equals f of x, then the area from minus a to a equals 2 times the area from 0 to a. For example, the parabola y equals x squared. If a function is odd, meaning f of negative x equals minus f of x, then the integral from minus a to a is 0. For example, the cubic y equals x cubed, where the positive and negative parts cancel out. So, symmetry can cut your work in half, or sometimes eliminate it completely. Whenever you're asked to compute area under a curve, here's the checklist. Step 1. Identify the boundaries, curve, axis, and vertical or horizontal limits. Step 2. Find limits of integration using intersection points. Step 3. Write the definite integral with correct orientation, f of x dx or g of y dy. Step 4. If the curve crosses the axis, split into regions and handle positive and negative parts separately. Following this flow ensures you never miss a region. Let's try a concrete example. Find the area under the parabola y equals x squared, bounded by x equals 0 and x equals 2. Step 1. Write the setup. A equals the integral from 0 to 2 of x squared dx. Step 2. Integrate. The integral of x squared is x cubed divided by 3. So a equals bracket x cubed by 3 from 0 to 2. Step 3. Substitute. At x equals 2, we get 8 divided by 3. At x equals 0, we get 0. So the final result is 8 by 3 square units. See how easy it becomes once you identify limits and apply the integral carefully. So why does this matter? The idea of area under curves extends everywhere. In physics, distance is found from velocity-time graphs and work is found from force-distance graphs. In statistics, probabilities are areas under distribution curves. In higher mathematics, these methods expand to surface areas and volumes. So the humble definite integral is not just an abstract idea, it's a universal measurement tool. And that's our session on area under simple curves. In the next lesson, we'll move to more advanced applications of integrals, like areas between two curves and surface areas of solids. See you there.